Okay, so Leetcode practice time. So in this video there are two goals. The first goal is to see how to solve this problem, and then we are going to do some coding work. And the second goal is to see how we should behave in a real interview. So let's get started. So remember, the first step in a real interview is to always try to understand the problem. If there is anything unclear, please bring up the question, and at the same time think about some edge cases. So let's take a look at this question. So all the nodes distance k in the binary tree. So we are given a binary tree, a target node, and an integer value k. So we want to return a list of the values of all nodes that have a distance k from the target node. So the answer can be returned in any order. So let's see. Example as root. So this is a root, which represents a tree, something like this, and the target is equal to 5 and k is equal to 2. So the output is going to be 7, 4, 1 because the nodes with distance as 2 from 5 is 7, 4, and 1. Okay, that makes sense. So let's see some constraints. So the given tree is non-empty. So it's not an empty tree, and each node in the tree has a unique value between 0 to 500. So the target node is a node in the tree. Okay, and k is between 0 to 1000. So first of all, we know that the tree is not empty, and it's for sure that the target is one of the nodes within the tree. But we don't know whether the k is actually valid or not, because if there's no nodes within the root within the tree that has distance of k from this target, then we are going to return empty. But I think that should be covered by the general algorithm. So let's see how to solve this problem. So the next part about finding solutions. So this part is mostly about you communicate with your interviewer in words, or draw something, whatever. So use any technique, any way to explain how you're going to solve this problem, and do some runtime space analysis. So let's see. For this, I would say first of all, we need to at least find the node from the tree. And then to find the distance from k, it makes me feel, to find all the nodes with distance k from this node, it makes me feel like it is a BFS function. It's a BFS problem. But the thing it's a little bit different from the regular BFS. It's because, except for the children nodes, we also need to extend to its parent node. So for example, for this node 5, the first layer we are going to try to include the left child, right child, and its parent. And for the second layer, we are going to extend the children's and the corresponding parent. So since this node doesn't have a parent, we are just going to expand to its right child. So I would say first of all, we could use either BFS or I think we could either use BFS or DFS to find the parent relationship for each node. For example, we find the parent of 5 as 3, we find the parent of 6 as 5, so on and so forth. So first of all, we need to run either BFS or DFS to find the parent relationship and add it into a separate map. And the next thing, we will do a BFS to extend from the target node layer by layer to try to find all the nodes that has distance k from the current target node. So having said that, the runtime is going to be all of n, because we just need to at most look at all the nodes within the tree twice. And so runtime is all of n, space-wise is also all of n. because we need to record the parent relationship, and potentially we also need to record which nodes has been visited in our BFS part. So having said that, let's do some coding work. So in the coding part, we care about the correctness of the code, the readability of the code, and also the correctness of the code. So let's take a look. So it's not an empty tree, and target is for sure to exist in this, in the tree. So first of all, let's define a helper function, call it DFS. So the DFS is going to have, you're going to have two things. The first one is a node, and the second one is the parent. Alright, so we are going to first of all define a map with tree node. So the first one is a node, and the second one is its parent node. So I will say parent node parent, new hash map. Alright, then we will run DFS on top of it. So it would be root and then a non-pointer. And actually at the same time we need to pass in the node parent, which is a map, into it. This is node parent. So node parent. Alright. So if node is equal to none, then we just need to return. Otherwise we will need to have node parent dot add, let's put node and parent. Then we are going to say DFS on top of node dot left and parent, node, and DFS node dot right dot node. So yeah, so that's it. And also we may not really want to have the pair, which is the root and the non-pointer put into it. So I will just put a if parent is not equal to a non-pointer, then we are just going to put the node and the parent into it. Yeah, so that's it for the DFS part, to have the parent node. Yes. And then the next part is about BFS. So for BFS, we essentially need to have a queue of the tree node. So the tree node, let's say it's a queue. We use linked list as the underlying implementation. So first of all, you put we add the target node into it. So while queue is not empty, then we are going to keep continue. So in this case, we actually need to keep track of, one is the distance, starting with k, and the other one I would need to keep track of is the, because we need to, for example, for 5, the first layer is 6, 2, and 3. We don't really want to visit 5 again, because we don't really want to visit the nodes we have already visited again. So we need to pretty much have a set of the nodes, let's call it visited, as new hash set. So first of all, we will have int size as the q.size, and then we are going to say I is equal to 0, I is smaller than size, and plus plus I. So if so first of all, we need to pop the thing. So tree node, the node as equal to q dot pop. Okay, it's full. Alright, so yeah, we actually need to define the thing we are going to return finally. So let's define the list of the integers. This is nodes with distance k. New let's say linked list. So if the distance is equal to k, then we need to have nodes with distance k is dot add it will be dot add node dot value. Okay, and then for how to extend it, so we would need to make sure that, so if node dot left is not equal to a none, then so if node dot left is not equal to none, then we are going to add it into the queue. But first of all, we need to make sure that the node doesn't exist. So if visited dot has dot contains, if visit doesn't contain node dot left, then we are going to have visited dot add the node dot left, and we are going to add the queue add node dot left. Alright, so this is the left branch, and the next thing is about right branch. Right is not equal to a none, then if not visited, so actually we could define another helper function. Let's say void add let's call it add node to queue. So essentially we have several different things. The first thing is a tree node to be added, and the second one is a queue, and the third one is the visited. So the thing is, if the node is equal to a none, then we just return. And if visited dot contains the node, then we are going to return. And if the node is not none, we haven't visited, then we are going to have queue dot add the node. So we could use this helper function actually to have node dot left and the queue and the visited. So similarly, we have a node to queue. This is node dot right queue and visited. And similarly, we will have the root dot Okay, so it's no add node to queue. I would say if the if node parent dot contains key, which is the node, then we will call the add node to queue node parent dot get, or maybe we just call it get or default so this is a node and the none pointer. Alright, so if the parent is now none and it's not in the visited, and we're going to add the parent into it. So yeah, I think that's pretty much it about how to extend this layer and about how to add the node. And finally, we are just going to return what is that? We're going to return node with distance k. Alright, so having said that, I think we are mostly code complete, but I think there is a bug here actually. We should plus the distance here, because we just visited one layer. We need to plus the distance, and after we plus the distance, if the distance is larger than k, then we pretty much just need to break this while loop here. So after we are done with coding, it's not done with the interview. We need to do some testing. So the way we do testing is, first of all, we do some sanity check by going through an example to see how it is going to work. At the same time, we are going to explain how this piece of code is going to work to the interviewer. And after that, we will introduce some different test cases to make sure we have good enough test coverage about different branches in the code. So let's see. Let's take this as an example. We find the target as 5, k as distance as 2 within the tree. So first of all, we have the node parent thing, and we have the DFS on top of it. And if parent is not equal to none, then we just put the node and parent relationship, and if node is equal to a none, then we just simply return. So first of all, we are not going to put anything when it's root, because we call the root none. Then we go to the left and right child. Yeah, so I think similarly we could, and then we are going to deeper and deeper. As we do that, we keep adding the parent relationship into the node parent map. So I think after that we should be mostly good about it. And after that, after the DFS, it's the BFS part. So we have the queue, we have the distance, we have the visited. So while the queue is not empty, so first of all we will have the size of the queue, which is the number of the nodes at this layer. So we are going to say, okay, node is equal to none. Sorry, node equals to we are going to pull the node from the queue, and if the distance is equal to k, then we are going to put it into it. So first of all, we pull the 5 from it, which is the first layer, and currently distance is equal to 0, which is not equal to k. So we are going to add the left, right, and parent into it. So when we try to add, we need to, actually I didn't update the visited, so we should have the visited dot add the node when we try to add node to the queue. So okay, so we update the visited, and we also update the queue. So currently we have the queue It has 3 nodes in it. The plus plus the distance because this layer is finished. And next time when we step into the while loop again, so the distance is 1. And then we are going to try to extend this node. First of all, we try to extend 6. So 6, we see that the both left and right are none, then we are not going to add into the queue. And we see that the node 5 is already visited, so we are not going to add into the queue. So for 2, similarly, we are going to add 7 and 4, but we are not going to add 5 into it. For 3, we are not going to add 5, and we are not going to add its parent because the parent is a non-pointer. And also we are going to add the 1 into it. And we are going to plus the distance, not distance is equal to 2. So the next time we have 7, 4, and 1 in the queue, we add the values and extend. After we extend, the distance is larger than 2, so we are going to simply break. So I think mostly it should work from what I can see. Let's give it a shot by running this piece of code. Alright, so what is this? It's node. Oh, okay, so I think I should, some typo here, it should also pass a node parent into it. Okay, so it's wrong answer. Let's see why it is wrong. So we got 5, 7, 4, and 1 into it. But should we do it? So I think the thing is we didn't add when we try to add the first stuff into the visited, then we didn't actually update the visited with the first node. This is essentially where the bug is. So I think this should fix the bug. So visited, so we should define it here. Should add a queue while we update the visited. Yep, so this should fix the bug. Let's give it a submission. Alright, so now everything looks good. So regarding the test case setup, I would say I think having this test case is pretty good enough, but if you want to keep some other test cases, for example when k is equal to 0 or when k is larger than when k is set up as a value that we will return nothing from the tree, so that would be great. But if you just set up this example, I would say that's perfectly fine. So that's it for this coding question. If you have any question about the puzzle or about the solution, feel free to leave some comments below. And if you like this video, please give me a thumb up, and I'll see you next time. Thanks for watching.